Hi everyone. I am Shrutitha Panda. We are from today we are starting a series of lecture for targeting CSIR NET June 2024 Chemical Sciences. So we will be covering almost 30 topics, which are very much important for the exam point of view. The From which topics actually the questions are coming in previous years. So that we will cover, and also the tips and tricks to solve the question in a better way and in a short period of time, and also the previous year questions will be solved. This 1 month is very helpful. This is very important for the students who are preparing, and we will like to deliver them a good strategy, and also some topics which will be helpful for their preparation purpose. So let's get started then. So for topic one, I have chosen one inorganic chemistry topic, coordination complex and isomerism in coordination complex. This will be a one short revision of the topic, and also these topics actually will be not very much descriptive. It will be to the point kind of lecture, and also the focus will be on majorly the how the questions can be tackled and how we can clear the CSIR NET exam. That will be our main focus, because time is less. Right now, only 1 month is left. So do good and all the best in advance. So let's get started with topic one. Hope you enjoy our my lecture and will be enthusiastic about these topics and other topics of CSIR NET exams. So let's get started then. So firstly, what is the coordination compound? So you must be thinking, right? No, not everyone, because we have actually in 12th class, we have actually read about this coordination. If you forget about it, don't worry, I will make you help to recall the topic. Okay. So to know about coordination compound, we have to have the idea about what is a coordinate bond. Okay. So first we know ionic bond and covalent bond. We all know, right? So what is happening here? One atom A and another atom B, both are sharing one electron, and these two electron actually combines and form one bond in between them. So one bond is formed. This is called covalent bond. And in the other hand, what is a coordinate bond? This is actually a type of covalent bonding, but here what is happening? The Where is the difference actually? So difference is here. One atom is sharing both the electrons to the vacant orbital of another. Okay. So the definition you can see in the slides, the same thing which I have told you. Okay. So now we are coming to coordination complex. So chemical compounds that consist of an array of various anions, neutral molecules that are bound to a central atom via coordinate covalent bonds. Okay. Don't You are getting confused? If I give an example of the coordinate complex, you will understand it in a better way. Okay, so please wait. So center atom, right? The center atom is generally a metal, more specifically a transition metal. What is transition metal? 3D, 4D, 5D series of metals, right? So, and the atoms or ions which donates its electron pair to the metal and forms coordinate bond is called ligands. Yes. So, two things we have read till now. One metal is present and one ligand is present, right? But how they are actually attaching and what will be the representation, you can see here. This is an example. So, this third bracket, this is used to represent a coordinate complex. Okay, this is the metal and this is the ligand. Okay, 6 amine ligands are actually donating electron to platinum metal. Okay, so this is the coordinate complex. You will understand. You have understood this, and so many of you are thinking that what is the Cl then here? It is also ligand. You are thinking, right? But it is not. It is only here to neutralize the charge in the coordinate complex. It is a part of coordinate complex, but it is not directly attached to, it is an ionic bond. Okay, so we will understand in better way in the next slides. So before that, some important features of coordinate compounds. The compounds has its own characteristics which can be different from their component molecule. Let's say H2O, right? We all know water. It is consist of hydrogen and oxygen. Okay, but hydrogen and oxygen are combining to form H2O, but it has different characteristics than the hydrogen and oxygen molecule atoms. Okay, so like the same way, the compound coordinate compound shows the its own characteristics. Okay, which can be different from their component molecules or atoms, etc. Okay, ions. So this is there, and also the compound can retain their identity. The compound can retain their identity in molten and solution phase. So let's take a real life example. So for your understanding purpose, so if you are a not a kind of talkative person, okay, so you are a shy person. So in you are, and now you are going to a party or wedding, okay, so where everyone is there, and let's take it as a solution. Okay, solution phase. In that phase also, if you keep your nature retained, like in this party also you remain shy and not, you are not talking to other persons, so then we can say that it can retain their identity like you. Okay, so let's take an example of ionic salt, NaCl. We all know in the solution phase it is forming Na plus and Cl minus ion. Okay, Cl minus ion. And if you take a complex molecule like PTNE3 full 6 Cl2, what it will give? It will give the complex will be intact. Okay, so complex part is coordination here. This will be 2 plus and this will be 2 Cl minus. Okay, in the solution phase it will be there. So it can be ionizable, but it is not. So now we have to see the parts of the coordinate compound. So this is the same example, right? So metal and ligand, I previously told you, and 6 is the coordination number. It is also very important. Okay, coordination number to find a geometry, coordination number is very important. Okay, and this is called actually primary valency. Primary valency. Okay, so Warner's theory are also there, but I will not go to that part because no, this is not important for our CSIR NET exam point of view. So we will be just the structural some characteristics will be fine for now. So this is a coordination number, and this part is actually coordination sphere, which I have told you inside the third bracket. And this is the ionization pair. It can be ionized, right? And this is secondary valence. Okay, so let's coming to the now ligand. So what are ligands? We already know the negatively charged or neutral molecules which can donate the electrons to the metal, right? So types of ligand, actually ligands can be classified in various way. So firstly, based on charge, let's take let's see the types: cationic, neutral, and anionic. Okay, so cationic example is NO plus, NH3H2O, F minus, Cl minus, are anionic. Okay, so these are some ligands, and based on denticity. So to know this, we have to have idea about denticity. I'll talk about it in the next slide, and you can see here various kind of ligands are there in this type. And third is the based on bonding. There will be sigma donor, sigma and pi donor, sigma donor, pi acceptor. Okay, these three type. Okay, now first is here only based on charge. It is not very much important. You can see here positive, neutral, and negative. You will know. And based on denticity. So to know it in a better way, so we have to have idea about denticity, right? What is denticity? Denticity is the number of atoms of ligand attached with metal. So ligand is a molecule, right? It has many atoms. So number of atoms, please remember this, number of atoms of ligands attached with metal, not number of electron pairs and nothing, number of atoms. Okay, clear? So monodentate, mono means one. Okay, so this will be donated via nitrogen, this will be via oxygen, like that way. So if it donates, the first donation will be sigma, through sigma. I will talk it in the next slide. So, and this will be pi donor, pi donation. Okay, but these two electron pairs are donated by H2O. If it happens also, we cannot say it is bidentate also. It will be monodentate only. Why? Because the atom oxygen is only donating. Okay, so number of atom is the most important thing here. Bidentate will be ethylene diamine, 2 nitrogen. You can see this glycinato ion. This donation donation will be from 2 atoms. And tridentate, there are some examples you can see in the slide. Tetradentate also there, 4 nitrogen atom you can see. Okay, pentadentate and also hexadentate. This is important. This is EDTA. You all know, I think. You all know because it is a chelating ligand. So this has 6 atoms which can be donated. This is hexadentate. Very much important. You must remember this name. Okay. This 4 and this 5. This is 6. Okay. 6 atoms for donation. Now based on bonding, sigma donor, which are sigma donor. So there are examples here written, but always remember every ligand first act as sigma donor. Every ligand it is. Okay. After that, sigma donor, pi donor. This kind of molecule must has 2 lone pair, at least 2 lone pair it should have. Okay, for 2 kind of donation. And this is sigma donor, pi acceptor. This is a different kind of ligand because we have read that ligands are only donated. The ligand can only donate the electron pair to a metal, but here it is sigma donor. Donation is there. First it will donate, but there is pi acceptor. It will accept electron from metal in its anti-bonding orbital. Okay. So examples are Cn negative, CO, NO plus, etc. Okay. So now few popular ligands I have shown some structure because it will be helpful because in the questions it will be not given the structure of the ligand, right? These kind of things are there. Fe, PHEN, whole 3, like that. Okay. So you have to have the idea about the structure or the donor sites, how many donor sites are there. So, okay. So this is ACAC minus, acetyl acetonate ion, oxalato ion. and oxalate ion, dimethyl dioxometo ion, ethylene diamine, glycineto ion, diethyl ethylene triamine, 3 donation, 4 and 6. Okay, so these are some important structure. You should, I will not say remember, but you have to keep this structure in mind, so that in the questions, when we are solving the questions, so it will be helpful for you. Now, this is not a classification, but a type of ligand. There is a type like ambidentate ligand. What is this? A type of monodentate ligand. It is monodentate, which has more than one donor site and can donate electrons to metal in more than one possible way. What does it mean? This will be monodentate, obviously, but it has more than one donor site, so it can choose to which site it can donate, right? This is ambidentate behavior, and this kind of ligand is called ambidentate ligand. Examples are isothiocyanate, thiocyanate. Okay. Donation site is nitrogen, this is sulfur. Cyanide is there. Through carbon it can donate, also through nitrogen it can donate. Okay. So cyanide, isocyanide. So these kind of examples are there. And another one is flexidentate ligand. Don't get confused. This was ambidentate, where it will act as monodentate only, but it has more than one donor site, so it can choose that from which site I have to donate. Okay, if you have money in various bank, if you have various bank accounts, but you have the power to choose that through which account money will be transferred, like that way. This is ambidentate ligand. And what is flexidentate ligand? A type of polydentate ligand which can adjust its density and can donate electrons through one or more than one donor sites according to the requirement of metal. So more important thing is it is polydentate. It can adjust its density and can donate electrons through one or more than one. What is the difference between the flexidentate and ambidentate? So ambidentate ligand is always monodentate, but here it is polydentate. It can donate with 1, 2 or 3, like it can uh, with the requirement of metal. So you have, like, it's a, let's say 100 rupees. Okay, so according to the requirement of the shopkeeper, you will give, right? If the the cost of the product is 20 rupees, will you give 100 rupees to the shopkeeper? No, right? So that is the thing here. You have many. If you have no, you don't have 1 rupees only. You have 100 rupees in your hand, but you are donating to the shopkeeper or giving it to the shopkeeper with the requirement, based on the requirement. Okay. So examples: sulfate and EDTA also. Various, any polydentate ligand you take, so it can act as monodentate also, bidentate also. This is hexadentate, na? You know, this is hexadentate. It can donate through this, to this, to this, to this, based on the requirement, the size of metal, the charge on metal, etc. Okay, these things are actually happening here. So let's not talk about much. So you have to have the idea about different kind of ligands. Okay, now coming to the how to calculate the oxidation state of a metal in coordination complex. So it is a basic in this chapter. Is the questions are coming from this only? No, but you have to use the idea. This idea will be helpful for the question solving. Okay, so it is basic for this chapter. I'll give some examples. So here, this is one example, this for this complex. So let's say the metal, the oxidation state of metal is X. Okay, so X we are taking. So that X is the charge on metal, right? Oxidation state, same thing. So X plus, this is, we know that this is neutral ligand, right? It has, it is a monorented ligand, but that is different. We are now calculating the charge, right? This is neutral ligand. So 0 charge is present here. So 0 into 6 equals to 2. Why 2? Because 2 chloride is there to balance the, to neutralize the whole compound complex. So here must be 2 plus is there, right? So by this way you can calculate the charge on the metal, it will be plus 2. Here is another example. So the oxidation state, let's say this is X, 0 into 4, as it is neutral. This is negatively charged, right? This is now inside the coordination sphere and whole charge is 0. So minus 1 into 2 equal to 0. X will be 2 again. Okay. But if you think that these two molecules are same, you are wrong. Because structurally also in this compound, the coordination in the coordination sphere or coordinated bonds are forming between platinum and 6 amines, not chloride. Okay. But here the coordinated bonds are formed between platinum and 4 amino and also 2 chloride. So these two are different, remember? So you should understand these kind of things properly. These are basic. Okay. So let's calculate it, the oxidation state for this. Let's take it X plus 5 into 0 plus minus 1 into 1, okay, equals to 2 negative. Sulfur always 2 negative. So here 2 positive must be present. So 2 plus 2. Okay. So this will be 0 and X will be 3. So here oxidation state of cobalt will be 3 plus 3. Okay. I hope you understood this because it is simple. Now coming to the important. This is important for examination point of view because questions are coming frequently in the CSIR NET exams. So isomerism in coordination complex. Okay, let's start it then. Isomerism. Two kind of isomerism is can be seen in coordination complex: structural and stereo. In the structural isomerism, there are many like ionization, hydrate, linkage, etc., etc. We will cover this all. And in the stereo isomerism, geometrical isomerism and optical isomerism. Okay, I will try to cover these all in this lecture only. Let's see. So structural isomerism first. Ionization isomerism. You don't have to remember anything in this structural isomerism topic, but the examples. Not there is no need of any description or anything. You only have to remember some examples. Okay, so that you have the idea about what is ionization isomerism. Because in the questions, many examples or many options are given, and you will be asked that which one is ionization isomerism, right? So you have to choose between the options that which one is correct. So for that only you should have the idea about what how we can identify. Okay. So see the example. What is the difference between these two? The same cobalt complex NH3 whole 5, NH3 whole 5. Till this is same, but here Br is present and here sulfate is present. And here sulfate is outside, Br is outside here. So what is happening here? So here only the exchange of these two happens here. This is called ionization isomerism. Okay, because it will affect only in ionization. When we ionize this complex, the sulfate will be will be there because sulfate will be released. And here if we ionize this one, let's say we are AgNO2 is given, so AgBr will be precipitated here, so Br minus will be released, but this whole thing will keep as it is. Okay, so for this reason it is called ionization isomerism. Next, hydrate isomerism. What is the difference between these two? Structurally, if you only see that how many of these molecules are there, so here 6 chromium is present, 6 water, 3 Cl. Here is also same, but see the arrangement, only water molecules are exchanged. Here in the coordination sphere 6 water molecule is there, but here only 5 is there, and outside the coordination sphere 1 water molecule is there. Okay, so this is called hydrate isomerism. Okay, linkage isomerism. Linkage means linkage between metal and ligand atom, the donating atom, right? Here only these kind of linkages we are talking about, na? Coordinate bond, coordination complex is all about the metal and ligand bond. Okay, so linkage isomerism is this. So NO2 and ONO. Here donating the same, all the things are same, you can see. But here donating atom is nitrogen. It is donated to it is donating its electron pair to cobalt, and here oxygen is donating to cobalt. Okay, this is linkage isomerism. Next is coordination isomerism. So you can see in this example, this is positive part of the complex. Here two complex are present which are actually neutralizing each other. Okay, this is positively charged. You can see this is neutral ligand is present, so it must be positively charged, and it is negative, Cn minus is present. So this whole complex is negatively charged. Okay, so these two are neutralizing each other. This is positive part, this is negative part. Only the difference is the metal is exchanged here. See, from this coordination sphere to this coordination sphere, only the exchange of metal you can see. Here in the place of cobalt, it is chromium is there, and here also cobalt is there in place of chromium. So this is called coordination isomerism. After that, coordination position isomerism. What is this? Position means there will be something regarding about the position, right? So here the bridging atoms, bridging ligands are also there, which are bridging between these two complex. So in this kind of complex, only coordination position isomerism can be seen. So this is a complex molecule. Okay. So what is happening? Exchange of some ligands to this. You see? Okay. This is happening. Cl is here. Cl is here. Cl comes here, and one amine group comes here. So this is coordination position isomerism. This is only seen in this kind of bridged compound. Okay, and then ligand isomerism. What is ligand isomerism? So when the ligands itself show isomerism, this is PN. Here this is carbon nitrogen bond. So 1,2 amino. Okay, 1,2 amino group is there, and here 1,3. This is TN. All the things are same, but just the amine groups are different. Both are bidentate ligands also. So here not the coordination spheres are same. The ionizable ions are also same. Only difference is the ligand. Ligands are showing isomerism. So here PN2, here TN2. Okay, this is the difference here. And so this is completed. So you just take a look. This is ionization, where the difference is in this only, which part is ionizable. In this part only the changes is here. Changes can be seen. In the hydrate isomerism, only the water molecule is exchanged between coordination sphere and the ionization sphere. Okay. And in the linkage isomerism, the the atom which is actually this ambidented ligands can will present like Ca and NO2 etc. And based on through which atom they are donating, based on this only linkage isomerism is can be seen. Okay, and here coordination isomerism, the positively charged and negatively charged coordination spheres are there, and only metal ion is exchanging. Okay, coordination position is for the bridging ligands, bridging compounds and bridging complexes, and ligand isomerism in the name is also written. This is based on the isomerism in the ligands. Okay, now coming to the stereoisomerism. So what is the difference between the structural and stereo? Structural will be based on the structures, like the connectivity of bonds and which are actually present in which ligands are present inside the coordination sphere and which are outside. Based on this, and stereoisomerism is different. This is the connectivity of atoms are same. Like in the coordination sphere, same atoms or same ligands are present, but their arrangements are different. Only the based on the arrangements. Okay, based on this is stereoisomerism is also there. First one is geometrical isomerism. Let's talk about this first. So coordination compound can have various coordination number. So from 4 it is started. If 4 is the coordination number, then two kind of structures are possible. One is tetrahedral complex and another one will be square planar. So we will talk about all these things in this portion. Okay. So first 4 coordinated complex, we are starting with simple one, right? So in the tetrahedral complex, you can see this is a tetrahedral structure. We all know this, right? So all groups are having same bond angles. So what we are saying when we are telling about stereoisomers, only the arrangements of the groups are different, right? But here, in the case of yes, geometrical isomerism is a part of stereoisomerism. Okay, where we are mainly studying about the angles between the bonds or between the atoms. Okay, or molecules. The angles actually matters. But here for tetrahedral complexes, what is happening is they all bonds here in this these all bonds are actually having same bond angles. So how can we differentiate between these? That these are in same side, these are in different side, or the bond angle are not same, right? So the arrangement, the spatial arrangement will not be different. It can rotate, right? How it will be different? It can rotate. So if you can here, if you incorporate C here A, but it can rotate. No? A can be here, C can be here, but all the angles are same. These also, these also, these also. Understood? In the 3D model, we'll understand in a proper way. In the 3D, let's see that. Okay. So no cis trans, no geometrical isomerism. Okay, fine. So square planar complexes. We are coming to what? Square planar. Type 1. What is type 1? MA4, like A is a ligand. Same type of 4 ligands are present, and MA3B. Okay. In this type, these two are possible. Sorry, this is the structure of these two complexes. MA4. Can we arrange this B in the other way or other position so that one new complex will be formed? No, right? Because one B is present here. This is cis 2B and trans. Oh, sorry. Cis is same side. Trans will be 180-degree difference. Okay. So if because let's take this example. This B and A are trans to each other. Why? The bond angle is 180. Like opposite. We are saying the opposite. So trans means this B is opposite to A, but it is near to A, this A and this A. Cis to this and this, but trans to A. If we place B here also, same thing will happen. It will be cis to this A and this A trans to this A. So we can't have another arrangement of these two molecules. Okay. So these two doesn't show any cis trans isomerism. Clear? Now coming to type 2, Ma2B2. This is different. Okay. So these two will be possible. Where these two B are cis to each other and all the B are trans to A, and another one is the B are trans to each other and A are trans to each other. These two are different, you can see, right? So these two are here. So when you will be asked that how many geometrical isomerism will be possible for this complex, you will say 2 cis trans. Type 3, Ma2BC. Same will happen. BC, this is not same group, but with respect to these actually we are arranging, right? These two are same, so we have to have the capture the easiest way. These two are same, so keeping these two as cis, and we have no other options. It is 4 coordinated, right? So we must seat these two or place these two in cis manner only. And here, if these two are trans, we have to place these two trans. So these are two only possible here. After that, the type ABCD. Okay, so possibilities are, let's say ABCD. We are taking where AC are trans, BD are trans. Okay, now we are changing. AD will be trans. These were C's, right? AD will be trans, BC will be trans. So AC trans, AD trans, now AB trans. Okay, these three possibilities are there. So combinations are, for in a short way, you can say AC, BD is only left, BD. Then AD, AD, and BC, of course, these two are left. Then AB and CD. Okay. No other combinations are possible, right? Now coming to the MAB2. Why this bracket? This bracket actually represent the single bracket. Represent that this is what? Bidentate ligand. This is, we are talking about square planar complexes, right? And this is 2 and AB are present. So both atoms are actually donating. So how we can draw these kind of structures? Here. So A, B are connected actually. This is bidentate. This is bidentate. So is there any other structure possible? Think. A are cis. B are cis. We can revert this, right? Yes. See, A are trans and B both are trans. Okay. These two only possible. Now coming to the 6 coordinated complex. So you must be thinking, right, like it will be more complex. Like we are studying complex compounds, and it will be complex obviously, but we have to find a easiest way to understand this topic, to solve the questions easily, right? 6 coordinated complexes. Type 1 is there. Type 1 where Ma6, Ma5b, Ma2bc, A4b, A4, this. Okay, these all will be. So how we can draw M, sorry, in A, 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 A. Octahedral, right? Octahedral will be geometry, right? For the 6 coordinate complex. So this is the structure. So all the ligands are same. So no geometrical isomerism because all the ligands are same, na? So we can't differentiate. If in the place of A, if we incorporate here B, will there be any difference? No, right? No other structure will be possible. Only this structure will be possible. But when we are actually incorporate the MA4BC, right? MA4, let this C. Then what will happen? Two structures are possible. How? It is trans, na, here. So one another one will be M A A B C A, right? So this is cis, this is trans. Okay. Oh, this actually we are drawing. Okay. Then MAA whole 3. M whole 3 means this is again the bidentate ligand, but here the donating atom are same. A, this, A, connected, A and A. These two are also connected, right? So here is also all the angles and all the atoms are same. So no isomers present. Okay. I think this is mistakenly I have taken here. So in this group actually all the in this group actually all the structures, all the complexes are having no geometrical isomerism. Okay. Now type 2. I have drawn this, right? BBR cis, BBR trans, right? Same way, this BC can be MA4 are same, right? BC can be cis and trans. So two are possible only. I am not drawing this. And MA3B3. So what will be the structure? You think this can be the structure, right? M, okay? A, 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 B, B, B. What is happening here? All the A is having same bond angle. This is 90. This is 90. Okay. This is also 90. This is up, right? Up, up, 90. And here B, the same case is for P or cis. Okay. And another, if we think about any other structures, what we will change? We can put one A2 trans, right? Then see what happens. Okay. We have taken this A and shifted to this. All the other all the other places there will be B, right? So here it is. These two are only possible. If you take any other positions and try it yourself in your copy, you will understand in a better way. So to understand it properly, what you should look, which are trans to each other or cis. Okay. So this A is trans to one A and cis to one. This all the A you can say no, one A is like that and another one is cis to this both two, and this is also trans to one A and cis to one A, like that way. So in the case of B is also same happening. If we try to draw any other structure, okay, I am drawing another one. Okay, so what E1? I'll take the A to this position or this. Okay, this A, all the others atoms will be there only. B, A, B. So where will be yes, another B will be here only. Look, same thing happens here. Trans to 1A, cis to 1A. This is cis to 1A, cis to 1A. This is trans to 1A, cis to 1A. Same thing is here. And in the case of B also the same thing is here. So only two structures are only possible. So these two structures are actually very much important. This kind of complex is very much important for the examination point of view. Is important because it, and for this also it has a different kind of name other than cis or trans. So this where all A are cis and B are cis. This is called FEC and this is called MAR, the other one which is possible. Okay, this is very much important. Now type 5, there is M, A2, B2, C2. Okay, I'll try to draw it. M, I will, when I solve some questions like this, I will try to draw or I will try to place the ligands first in a cis manner, all cis. Okay, all cis manners. So here you can also use the same thing, right? Cis, cis, cis. Okay, then I'll try and place one of the three atoms trans to each other. A, A. Let's say A, I am taking trans. Other four are possible. There is various possibilities. I can take B cis, and if I take B cis, two are only left. So I have to take C as cis. Okay, one, two have I have drawn, and here third one will be what will be. Let's say okay, A at here, right? So we can take A trans, B where cis, B can be trans, C can be trans. Okay, this is whole trans, this is whole cis. Any other possibilities? Yes, of course. Because you can see here, we have taken A as trans. Like the same way we can have, we can take B as trans or C as trans, and other groups are remaining as cis. Here all trans. So it is only one possibility is here, but here in this structure there are two other possibilities. How? B, B, and C will be cis, A will be cis, and here another one C will be trans, and A will be cis, B will be cis. Simple. So how many are there? 1, 2, 3, 4, 5. 5 possibilities, right? So any other possibilities? Let's check once. This is cis, all cis. This is trans, but one group is trans, and three are present, so there is three structures, and this is all trans, so 5 geometrical isomers are present. Okay, and in this case actually 15 types of geometrical isomers are present. All I will not draw, but there are combinations, like right, so AB can be trans, and we can play with other groups, and AC can be trans, we can play with other groups, and AD can be like that way. Okay, so 15 types of isomers are there. Confusing, right? But not much. If you draw the structures carefully, you'll understand how. First, try to place all cis forms, the ligands in all cis form, and then try to try to look at the structures and try to find possible ways like this way, right? I have told you. So let's not be confused, because optical isomerism is also there. So let's not be confused so much. So I hope you understood it properly. This is only about the bond angles, and you have to play with different combinations, starting with all C's, and then make first one group make C's trans and others remain C's. Then another group, like that way. Okay, so you can play with that. I hope so. So now, okay. So another types are there where the bidentate ligand, yes. So bidentate ligands are present. How I can draw it? Okay, no, not only the bonds I am drawing first. So A can be here. I'm just putting in a rough way to and possibly I am just putting in. I have started with one direction. If you remember when I was solving the previous questions, A. Okay. Then what is left? B. This is one possibility. So I always start with this one, then play with others. What is the other possibility? What is or are? So first, I am seeing that this is cis. So I want to put it trans. Then what will happen? A is bidentate here. A. Okay. So any other possibilities? This A are also trans. This A are also trans. These two atoms are same, na? So no. There is uh, nothing actually left. If you see clearly, this B also sees this group. We can't actually change it. Okay, so there is two possibilities, two, and here if it BC, same thing happens. Only in the place of B, here C will be present. The same two isomers, geometrical isomers will be there. In the case of this, in A3, AB3, okay, let's try. Okay, sorry. I am starting with this side, AB. Okay, I have to take AB because it will be bidentate and it should actually lie or sit near each other. Okay, now again AB I am taking simply, and then again AB. Nothing wrong with it, right? Now let's see if there is any possibility. Okay, let's try and draw AB. Okay, let's say I am changing it with BA. Okay, and I am keeping this as. Is it different? Yes, obviously, because here A trans, one trans is there. Here all A are cis. Here trans A we can find, and also yes, trans B. Okay. Any other possibilities? Let's say I have changed this one, right? This I am keeping fixed. This one I have changed. If I change the other one, BA, same thing will happen. BB trans, AA trans, right? Same thing. So I have to erase it. Okay. Any other possibilities in your mind? Okay. I am reading your mind. Let's say these both I will reverse. Okay. Let's see what BA and here also BA. AAR trans, BBR trans, ABR trans. BB trans, AB, same structure it is. A trans, BB trans, AB trans. Here is also same thing. So same structure. So there are nothing left, right? These two only possible. That's geometrical isomerism. Okay. So now, yes. Again, this speck and mark, like the same kind of thing. Why it is here? Because like the same way, here is also face and facial and meridional. The full forms are here. So like the same way, actually we can arrange it. Okay. So okay, this then coming to a question. What will be the number of geometrical isomers in the complex AB2, AB2, B2? AB2, B2. Okay. So what is here? AB ligand is here, which is bidentate, and two other B ligands are there. Okay, 2B and AB, AB. Let's try to draw, okay? Because other than that you will get confused if I say only. So first, what I told you, AB, I put AB. Again, AB is there. I put AB is there. AB there, and only BB, 2B are left. So I'll place that also. Any other possibilities? Okay, so these two B are Cs. Okay, we can take this B2 as trans, B and B trans, right? If we take this 2B as trans, there will be AB and this is AB. We can take this, right? They are bidentate. We can take this. Where these 2B are trans, but not A. A are cis, B are cis. So there is another possibility. Try and draw. B trans and AB. Sorry, AB is there, and here I am reversing it like the same way. BA. Is it different? Yes, because it is all trans. B are trans, A are trans. This B also trans. This is whole trans. This is whole cis. This is only B is trans. So three possible isomers are there. Answer will be 3. Any other possibilities if you see? No other possibilities, right? Don't get confused by seeing the structure. Just take these in a simple form, ligands. They treat them like these ligands like two atoms and attach it with by taking first with one side and then change the uh, the one by one atoms. Okay, then we will get the structures. Don't get confused. Now stereoisomerism. Okay, stereoisomerism we are talking of geometrical isomerism. Now it is optical isomerism. So first, to know optical isomerism, to know about it, we have to have the idea about optical activity. What is a optical activity? Okay, so the property of a molecule to rotate the plane polarized light. This you all know, right? I don't think that I have to explain it. So when a molecule is said to be optically active, yes, this is important because this is not a description or something. This is actually the thing which will be needed for the question solving. When a molecule is said to be optically active, when we will call a molecule optically active? If it has a non-superimposable mirror image. What does it mean? Let's say this organic molecule I have taken. This is a mirror. You have reflected this molecule in the mirror. Then this kind of structure is formed. If we take this whole structure and place it here, okay, over the structure, over this mirror image, these two will be different, right? Here F is in right side, Cl is there, here Br is in left side, here Br is in right side. So this will not superimpose to this, so it will be optically active. But if I have a question that is this a molecule is optically active or not, any molecule, so will I take a mirror and imagine like what will be the mirror image and then place it in over to the mirror image, and like that way will we solve the question? No, right? Because it will be very much time taking method, and also it will your mind will be frustrated till then. So look for a plane of symmetry. If a compound is given to you, draw the structures. Look for a plane of symmetry. If present, optically inactive. If not, optically active. What you learn in this slide? Let's see the molecule, draw the structure, look for if it has any plane of symmetry. If you get any plane of symmetry, if you see any plane of symmetry, this will be optically inactive. If any plane of symmetry is not there, then it is optically active. Okay, you'll understand it by the question solving. So first, 4 coordinated complex, again for the optical isomerism also. Two possibilities, one is tetrahedral, one is square planar complex. So in the case of tetrahedral complex, if all the ligands are different, like here B, C, D, F, okay, not only B, C, D, F, the metal center becomes chiral. Then we call the metal center as chiral. Then it will be optically active. Okay, this is the condition for tetrahedral molecule to show chirality or be optically active. Okay. So now coming to the square planar complex, what will happen? This is a square planar complex. Okay. It has a plane of symmetry. How? Let's take the okay. So like let's take the whole molecule A. Let's take this whole molecule here. Imagine it like the whole molecule. So this is a plane, right? Plane. Not a no upper bond is present, no down bond is present. So this is plane of symmetry is present. Always a molecular plane is there in the square planar complexes. So it has a plane of symmetry for all the cases. So it doesn't show any optical isomerism. Okay. So it ends here in the case of optical isomerism. So you will be happy to know that no other examples of square planar complex you have to solve. Okay, but there is 6 coordinated complex. 6 coordinated means octahedral complexes. Okay, the optically inactive, which are optically inactive. So this example actually is wrong. Okay, these all M. Why it is optically inactive? If I draw this, you will understand. Okay, let's draw this one. B is there. Okay. So this is up bond or axial bond. This is also axial bond. What will happen? How here is plane of symmetry is present. If we look carefully, that if we can see that this is here a plane of symmetry. Why plane of symmetry? Because in the left side there is 2A present in 90-degree angle. Here is also in the right side 2A atoms are present in 90-degree bond angle. So same thing, like a mirror plane. So the plane of symmetry is like a mirror plane, right? So this will not be optically active. This will be optically inactive. For all the cases, the same thing is happening. But for MA4B2, two possibilities were there, right? Cis and trans. So for the case of trans, you can again see that here is molecular plane is there, which can reflect the two B atoms here. This B, this is molecular plane. Okay, so it will be optically inactive. Optically inactive. But in the case of cis, is there any plane of symmetry? It can be like this way. Not only this and this can be this way. Corner portion also the plane can be there. So if we take, let's say, one plane which consists of the B, because these two are C's now, so we can't place a plane in between this. But if we imagine a plane that will be covering this 2A to B, okay, then this plane will be reflecting this A and this A. Hope you understood it properly. This B, A, this. Okay, let's clear it and draw it again. Okay, so this is the plane. Like this way. And it is reflecting two A atoms. These two. So it has a plane of symmetry. So it will be also optically inactive. Inactive. Okay. Yes, optically inactive. So Ma4BC, the same thing happens, right? Ma4BC. So Ma4BC, if I draw, okay, I'll draw BC trans. I am drawing first trans. Okay, this molecular plane is absent. Like it is reflecting B and C. These are two different things, two different atoms. But if we see the other way around, if we see this plane in between this in between this one here, you see this plane which is cutting this angle, okay. If you see this plane, in this plane B, C are present, but it is cutting these two halves, okay, where in the left side also A molecules are present in 90-degree angle, in right side also A molecules are present in 90-degree angle, okay. So in the case of trans, this will be optically inactive again, and in the case of cis also, like here BC, if we place, again same plane of symmetry is there and it will be also optically inactive. But what will be for this kind of facial and meridional? Optically active it will be, because all are cis. So you can imagine this plane is not possible. Okay. In between this, think about in between these two. It is there. This plane is actually cutting here in between these groups, and this is reflecting uh, A and B and B. Okay? So if you think that the same way, if the mirror or a plane will be cutting these two angles here from here, yes, there is this will be also optically inactive. Inactive. In the case of Mar, what will happen? Meridional. Meridional also, yes. It will be also optically inactive. How? Let's take a mirror from this. Okay. It will reflect this one and this one as well. Okay. So it will be actually optically inactive. Both are optically inactive. Now Ma2B2. there are few possibilities. I have shown you 5 possibilities are there. So for these cases, let's think what will be which one will be optically active and which one will be optically inactive. So let's find any plane of symmetry here. This will be not in between these two angles AC and BB. No, it will reflect A and C, and okay, it will not happen like that. No, this will be optically active. No plane of symmetry is there, right? If we cut this one also, this will reflect A and B. Not possible. Okay, here I am doing it with you only. You should also practice it. This is not possible. This one is not possible. But if you see this through this corner, if you, oh sorry, this corner, if you imagine a plane, okay, it will reflect B and B, same. So it will be optically inactive. In the case of this, same thing will happen. If a mirror is placed here, it will reflect C and C, optically inactive. And here also same thing, optically inactive. And here it is trans, obviously it will be optically inactive. Because it will, many planes are possible here, many planes. Okay. So now coming to the aim ABCD, I have told you that in the geometrical isomerism, 15 possible isomers are there, and all are optically active. So as a total, optical isomers possible is 30, because all having enantiomers, mirror images. So 15 into 2. The molecules which are optically active, it has a mirror image which are not superimposable possible, okay, with the molecule. So it consists of enantiomers, okay. So you have to consider, so if okay, let's say one question is asked that this molecule, how many geometrical isomers it will give? 5, right? I have drawn to you all the isomers previously, okay. But here it is optically active. It has enantiomers, the mirror image. It is optically inactive. No, it has superimposable mirror image. So same molecule. This is also optically inactive, optically inactive, optically inactive. So total number of stereoisomers, what it will be? 1, 2. Geometrical plus optical stereoisomers. In the questions also we will talk about this. Optical plus geometrical. So geometrical is 5 is there, and it is optically active. So it has 1 enantiomer. So total 6. Okay. So here is also 15 possible geometrical isomers, each of them having 1 enantiomer. So as a total 30, right? So various types are there. These two actually it has actually drawn. So here you can see, yes, one plane is present. So it will be optically inactive. Here, no. If you see these kind of bidentate ligand as that kind of atoms, it will not go happen like that, because in between these kind of bonding there is CH2 molecules and other molecules, carbon, hydrogen, can be oxygen, CO bonds, many things are there. So you should not seeing this AA bidentate ligand as only A and A, because here many things, many atoms, many molecules are here. Okay, so in this cis form, this kind of mirror image is not possible, because here it will reflect not only AA, but also here is this kind of chains are there. Okay, it is cutting the chain, this kind of this mirror image, and it is upside. Okay, so you are thinking like how this kind of bonding is happening. So let's say This is plain. 4 atoms are here. Okay. And axial bonds are like this and this. This is octahedral. So I am keeping this like this. Okay. So one bidentate ligand like AA, which okay, this, okay, octahedral. Now the one AA will be this and this, like that way, and another one is side by. Okay, so you can see the difference. Side by means here is one present, here is one present. So you can see the differences. Okay, so every time when you see bidentate ligand, don't get confused and don't think it as monodentate atoms. Okay, think like in 3D model. So in this plane, if it is like this way, another two AA are like this way. In the same plane, it is through this plane to upside. Okay, so always imagine like 3D models. So as I don't have any models, I have to show you like that way. Anyway, so it will not have any kind of mirror plane. So it will be optically active, of course. Okay, A may be 3, maybe 3 is also there. Okay, it will be optically active, obviously, because bidentate ligands are there. So okay, so A, B, A, B, A, B. Okay, no plane will be possible. No plane will be possible. And if the another form also we have we draw A B, this will be B A, and another one will be A B. No plane is possible. You can see because it is 3D, right? One is this kind of, one is this, and another one is below the molecular plane to below, molecular plane to up, and inside the molecular plane. Okay, so these three things are arranging like this manner, like a flower, so propeller shape. So I'll not say propeller, but you can imagine it like that way, right? So it will be optically, both are optically active. Okay, now coming to the questions, PYQs. Okay, so so that you can understand it in a better way. So here A meet 3 BCD, where A, B, C, D are monodentate ligands. The number of enantiomeric pairs of the complexes. Enantiomeric pairs they want, means they want only optical isomeric pairs they want, not the total. Okay, so let's draw this. So 3A are present and B, C, D. Okay, simple, right? No bidentate ligands are present, so it is simple. A, B, C, D. Same way, which I actually have talked to you. Okay, and again, so what I can do? I can do A can be trans. All the things I will keep in the same. B, C, D. In the same structure, you can see A are trans. Okay, B, D are trans, A, C are trans. It can be changed, right? In A, keeping A here, and C was there. It can be B, and D, C. Can be D. Okay. So AB trans, CD trans. Again, M, A. Okay, AB was trans, AC was trans, but AD has the also it is a combination, right? So AD and BC, CD, CD same thing, right? So these kind of things are there. Any other combinations? Any other combinations you can say? Think about it like this way. If you see the enantiomeric pairs, which we should talk about. Okay, so enantiomeric pairs. So now we have to consider all the structures and see about the optical activity. Okay, here no plane of symmetry is present. The molecular plane, no. Here in the corner, no. Here, no. CD, right? No, no possibilities. Optically active, obviously. Here, it has a plane of symmetry, right? Yes. These two can reflect. Optically inactive. Optically inactive, optically inactive. All are optically inactive. Okay? So only it is optically active. It has enantiomeric pairs. So the number of enantiomeric pairs for the complex is 1. 1 will be the answer. Understood? So again the question from CSIR NET November 2020. The number of geometrical isomers in this. Don't get afraid of seeing the molecule. Okay? Because this will be like, if we can simplify this structure, the rhodium complexities. So let's say this is metal M. Hydrogen is one ligand like A. This ligand is 2. It is the number is 2, right? MAB2. This one is C3. Okay, MAB2 C3. So now we are trying to draw the structures. Okay, many structures will be possible, I think. Okay, let's see. M M A B B C C C. Okay, so here A C are trans, B B are C, C C are cis. Now, if we take the combination A B is trans. AB can be trans, right? So B1 is present and one C will be here and C C. One C is trans, one C is cis. Okay? BC. Same thing is there, only AB is different. Okay, M. Another one. Think about it. We'll understand it. So AC, AB. AC, AB. Okay? AC, AB, AC, AB. Yes, yes, I found it. So here, no other possible way, right? So I have taken this B also trans and C also trans. So this, looking at this is done. Now within this structure, I have to find a different way. A C are trans, but B B are cis, C C are cis. We can take this, right, as trans. Let's try. B B C C, all trans. Okay, hope you understood. So is there any other possibilities? There are C's, they will be trans, and here these two are C's, trans, sorry, and these are no other possibilities. Three geometrical isomers will be possible. Okay, look how easy these questions are. So these will be answered. Among the following complexes, COOX, OX means oxalato, trans COEN. Okay, so you can understand here why I put the slide of the various ligands, structure of various ligands in the previous. Why I put any one slide of this consisting of the various ligands, like this way questions are actually asked. Oxalate, you have to remember not only the whole structure. If you are not recalling the whole structure, that will be fine, but in oxalate molecule both oxygen negative atoms are there, that you should understand. Okay, so CO, oxalate, O, O, this, O, O, this, O, O, this. Okay, but other atoms are also there. Okay, let's not talk about. And here trans 2-en, ethylene diamine. We know ethylene diamine has two donating center of nitrogen. Okay, ClCl. This trans, the trans, it has a chiral one. You have to find. It has a molecular plane. Okay, and it is reflecting on Cl and Cl. So it is not chiral. Here, chromium EDT. EDTA, it will be obviously chiral because EDTA is hexadentate ligand. It has 4 acetic acid and 2 nitrogen centers. So it is obviously not having such a big structure. It doesn't have, and in the octahedral complex, it has 6 coordination sites. So in this big structure, it is not possible, right? This nitrogen, nitrogen, here oxygen, oxygen, acetic acid bonds are there. So 3D kind of various branched will be there. Okay, so there is no possibility of having molecular plane. So this is obviously a optically active molecule, and this will be optically active. Okay, because here no plane of symmetry is present. This will be not present because why it is not present? If we think about this molecular plane, which is dividing these two bond angles, in between these two bond angles, right here, this kind of plane. Okay, this is reflecting this oxygen and this oxygen. This is fine, but here what is happening? This oxygen has bond with this oxygen. Upside oxygen has bond is in this way, and this molecular plane oxygen has bond with this. So this molecular plane will not reflecting this upside and downside bonds. If we think in a 3D manner, you will understand. Let's take this. Okay, one bond is upside and another bond is downside. How we can it can reflect to each other, right? So that is the thing here. So it is optically active, optically active. So what will be the answer? A, not B, C. A and C. C and A. Yes, this will be the answer. So you have read. We have learned to feel the isomerism, the every possible examples, and there are other examples, but I have shown to you various way to solve this kind of problem and to see the structures in a easiest way. Okay, and imagine the structures and to select the optically active one and optically inactive one. So I hope you find this video interesting, and thank you for watching this video. Thanks a lot, and please share your responses, and that will be helpful for me. So hope you understood the everything here. But if I forget anything, or if I any questions you have, you may ask on the comment section. Thank you so much.